Vector quantization is a block quantization approach. In this approach, we exploit the correlation between the samples of the source output vector of a certain length k in order to place the output points of the quantizer in appropriate position in k dimensional space. In today's class, we will study yet another block quantization approach. In this approach, we group the source samples in form of a vector of a certain length and then use a linear reversible transform to transform this vector into components that are then quantized according to the individual characteristics. This approach is known as transform coding. Before we examine the mathematical delicacies of transform coding, let us try to understand the working principle of transform coding and appreciate its advantage with the help of a couple of examples. Let us start with an example where a source generates a sequence of pairs of numbers. Now, from this sequence, we form source output vectors of length 2 by associating the first component of this vector with the first number of this pair and denoted by x0, and the second component of this vector is associated with the second number of this pair and denoted by x1. So, a typical sequence from such a source is shown here. Now, each of this source output vector can be represented as a dot in two dimensional space, where the horizontal axis represents x0 and vertical axis represents x1. Now, if we do this, we get the following plot. Now, let us make some observations about this plot. First, in the coordinate space xy as shown here, where x axis align with x0 axis, then in this xy coordinate space we find that this dots which represent the source output vectors cluster around the line y is equal to 2.5 x. Another observation from this plot is that horizontal coordinate is correlated with the vertical coordinate. Another observation is that except for the different means, the distribution of the horizontal coordinate is very similar to the distribution of the vertical coordinate, and the variance of the horizontal coordinate is very much similar to the variance of the vertical coordinate. Now, as we have studied earlier, that entropy, at least for Gaussian source, is directly proportional to the variance. So, what this plot indicates is that the entropy, which is a measure of information for the horizontal coordinate, is similar to the entropy of the vertical coordinate. And because horizontal coordinate and vertical coordinate are correlated, what this implies is that if we quantize the horizontal coordinate and vertical coordinate separately, then the outputs of these quantizers will have lot of common information. and this will not be an efficient way of transmitting the pairs of these samples or storing this pair of the samples. So, what should be done? So, one approach is that we take this coordinate space denoted by x0, x1 and rotate it about 0, 0 of xy coordinate space by angle phi. Now, if we do this, then this is equivalent to the rotation of the set of original sequence value by the transform y is equal to a x, where x denotes 2D source output vector and A is the rotation matrix, where phi is the angle between the x axis and the y equal to 2.5 x line. And y is the rotated or transform set of values. Now, in this case, the original axis x0, x1 have been rotated to the new axis y0, y1 by an angle of approximately 68 degrees, which is tan inverse of 2.5, and for this case we get the rotation matrix A given here. Now, once we have the rotation matrix, we can transform it and obtain the output as shown here. So, we get the output y0 and y1. Now, the next step in transform coding is to quantize this outputs y0 and y1. Let us assume that we use the same quantizer for both the components y0 and y1. We use a uniform quantizer and quantize it to the nearest integer. If we do that, then what we get is the following result. So, y0 cap is the quantization of the values y0 to the nearest integer, and y1 cap is the quantization output of y1 to the nearest integer. Now, from this y0 cap and y1 cap, we can obtain back the original sequence to some approximation by using an inverse transform in the form of A inverse. Now, if we did that, then we are not gaining any real advantage from the transform coding, except for the fact that earlier we would have quantized x0 and x1 sample, but now we have quantized y0 and y1 samples. So, if you want to gain the real advantage from the transform coding, then in that case we should exploit the characteristics of y0 and that of y1. Now, in order to study this characteristic, we could plot these points in y0, y1 space. But now, since y0 cap is very close to y0 and y1 cap is very close to y1, for the sake of convenience, we plot the points in y0 cap and y1 cap space. So, on doing so, we get this plots in y 0 cap and y 1 cap space. Now, the characteristic depicted by this plot very well resembles the characteristic of the points in y 0, y 1 space. And from this plot, we can observe the following. If we define the energy as the sum of the squares of the horizontal coordinate plus the square of the vertical coordinate, then this plot shows that almost all the energy is compacted into the first element of the pair indicated by y 0, while the second element of the pair indicated by y 1 is significantly smaller. Another observation is that now y 0 and y 1 are decorrelated. Another observation is that the distribution for y 0 is very much different from that of y 1. The variance of y 0 is much larger than the variance of y 1, and therefore, as discussed earlier, the information contained in y 0 is much higher than the information contained in y 1. And now, since y 0 and y 1 are decorrelated, there is very less common information between the two components. Now, as said earlier, that if we really want to get the advantage of transform coding, then we should use this characteristic to quantize y 0 and y 1. So, based on this result depicted by this plot, let us do the following. Let us quantize y 0 as y 0 cap by using a uniform quantizer, which quantizes to the next nearest integer, and get y 1 cap as the quantizer output for y 1, which is all 0. Now, what this means that we have set all the second elements of the transformation, that is y 1 to 0. Now, by doing this, number of elements that need to be coded reduces by half. Now, the question is, what is the effect of throwing away half the elements of the sequence? And now, we can answer this question by taking the inverse transform, that is inverse rotation of the reduced sequence. So, x 0 cap and x 1 cap denote the reconstructed sequence or the approximated original sequence, which is obtained by a inverse operating on y 0 cap and 0, because y 1 cap has been reduced to 0. If we do this, the approximated original sequence or reconstructed sequence is shown out here. And if we compare this reconstructed sequence with the original sequence, this is a table which depicts that. So, this is the original sequence and this is the approximated or reconstructed original sequence after we throw away half the number of components of the transform coefficient. Similarly, this is the reconstructed second component of the sequence and this is the original second component of the sequence. Now, comparing the reconstructed sequence with the original sequence, we see that even though we transform only half the number of elements presented in the original sequence, the reconstructed sequence is very close to the original sequence. Now, let us take another example where the source is an image. So, let us see how the transform coding works on images. So, the first step is to obtain the source output vector, and this is done as follows. For our discussion, we form source output vectors of length 2 by dividing the image into 1 by 2 blocks. Though in practice, typical transforms will use the block size of 8 by 8 or 16 by 16. So, this vector x will be either of size 64 or 256, and it is obtained by scanning these blocks from left to right and top to bottom. So, for our discussion, we will assume that we have 1 by 2 blocks. So, our vectors are of length 2. Now, using this principle, and if we take the source image as Lena and plot the source output vectors as shown here, with x1 representing the horizontal axis and x2 representing the vertical axis, then this is the distribution of the source output vectors, that is the distribution of adjacent pixels. From this plot, it is very clear that most of these points cluster around the line x2 equal to x1. Now, let us see what happens if we rotate this axis by 45 degrees by using this transform. The difference between this transform and the early transform is that now we have 45 degrees instead of 68 degrees. And when we do this and we plot the transform components in y1, y2 space, this is the plot which we get. Now, let us study the characteristic of this distribution before rotation and after rotation. If we look at the distribution of x1 before rotation, it is given here, and if you look at the distribution of x2 before rotation, it is given here. And so, from this distribution, we find that the information contained in this and in this distribution is more or less similar, and because x1 and x2 are correlated as depicted by this plot, it implies that there is a lot of common information between the adjacent pixels. So, it will not be wise for us to quantize them separately. Now, on rotation, for this plot, if we look at the distribution of y1, this is what we get, and if we look at the distribution of y2, this is what we get. So, again we note that the variance of y2 is much smaller than the variance of x2. So, if we adopt the similar strategy what we did in the earlier example and throw off all the y2 components and reconstruct the image by using just y1 component, we would get the similar results. So, the reconstructed output image will be very close to the original image. This is because the variance of the second component is very small when we discarded it. So, in both this example, what this rotation matrix A does is basically to compact the energy into the first component. So, for example, if we choose the transform A equal to 1 by root 2, 1 1 minus 1 1, and have the input vector x is equal to 4 5 to obtain the transform vector as now, what this shows is that the energy in the x, which is equal to 16 plus 25 is equal to 41, and energy in y, which is 6.364 squared plus 0.07 squared is equal to again 41. So, both the energies are same. We will very shortly prove that this is because of the kind of transformation which we have chosen here. Now, what is important is that this transformation makes the second component very small. So, in the original vector, if we discarded minimum component of the vector x, we would have an error of 4 squared by 41 is equal to 0.39. But now, in the transform space, if we discard the minimum component of the vector y, we have an error of 0.07 squared divided by 41, which is equal to 0.012. So, the conclusion is that we are more confident to discard minimum of the transform vector than the minimum component of the original vector. Now, in both the examples, we could reduce the number of samples we needed to code, because most of the information or energy contained in a pair of values was put into one element of each pair. Because the other element of the pair contained very little information, we could discard it without a significant impact on the fidelity of the reconstructed sequence. Now, in both these examples, we formed a vector of length 2. Now, if we extend this idea of forming vectors of larger length by incorporating larger block of source samples, then we would get the following result. By compacting most of the information or energy in a source output sequence into a few elements of the transform sequence using a reversible transform, and then discarding the elements of the sequence that do not contain much information, we can get a large amount of compression. So, this is the idea behind transform coding. So, if we ask why use transform coding, then we can answer as follows. The purpose of transformation is to convert the data into a form where compression is easier. This transformation will transform the pixels which are correlated into a representation where they are decorrelated. So, this is a very important aspect of transform coding. The correlation existing among the samples in the source output vector on transformation, they get decorrelated, and because they get decorrelated, we can independently quantize this coefficients. So, the new values are usually smaller on average than the original values, and the net effect is to reduce the redundancy of representation, because now we have minimal amount of common information between the transformed coefficients. And usually transform coding is used for lossy compression, where the transform coefficients can now be quantized according to the statistical properties which differ from coefficient to coefficient, and in the effect producing a much compressed representation of the original image data. So, if we were to put in a nutshell, the idea of transform coding is as follows. Transform the input pixels x0, x1, x2 up to xn minus 1. This implies that we have made a block of size n into coefficients y0, y1 up to yn minus 1 without loss of generality. We will assume to be real values. Now, if we have chosen the transform to be proper, then the net effect would be that the coefficients have the property that the most of them are near 0. In the earlier example, we saw that the second component was very near to 0. So, what it means that most of the energy is compacted into a few coefficients. Next step in transform coding is to scalar quantize the coefficient, that is, do the bit allocation. Important coefficients should have more quantization levels. That is how we will carry out the quantization. And finally, we entropy encode the quantization symbols and transmit it or store it. At the receiver, we apply the inverse transform. So, mathematically, this process of transformation can be depicted as shown here. We get the sequence y from the sequence x. Each element of y is a linear combination of elements in x. So, we see that the transform values are actually the coefficients of an expansion of the input sequence in terms of the rows of the transform matrix. So, that is why the rows of this transform matrix are often referred to as the basis vectors of the transform, and the elements of the transform sequence are often called the transform coefficients. Now, different transforms have different basis vectors. Sometimes the element of the matrix are also called the weight of the linear transform, and in practical application we want this to be independent of the data, except in the case of Carhon-Loy transform, which we will discuss very shortly. Now, the next question is, how do you choose the weights of these basis vectors? So, the general guideline to determine the values of A is to make y0, that is the first component of the transformed vector, to be as large as possible while remaining y1 up to yn minus 1 to be as small as possible. So, what this implies that the value of the coefficient will be large if weights a j I reinforce the corresponding data items x j. So, if this weights reinforce the data items, then this coefficient will be high. Now, this requires the weights and the data values to have similar signs. The converse is also true. Y j will be small if the weights and the data values have dissimilar signs. Thus, the basis vector should extract distinct features of the data vectors and must be independent, and we also want it to be orthogonal or orthonormal. We will see the reason for this very shortly. Now, what these basis vectors do in fact is that they pick up the low and high frequency components of this data, and normally the coefficients decrease in the order of y0, y1 up to yn minus 1. And because of this, y is now more amenable to compression than x. So, let us look at the choice of this transform. In both the examples which we considered, we find that the rotation matrix is orthogonal. What this means is that the dot product of a row with itself is non-zero, that is ai dot aj is non-zero if I is equal to 0 and is equal to 0 otherwise. The dot product of different rows is 0. Furthermore, we want that the rotation matrix is orthonormal. What this implies is that the dot product of a row with itself is 1. For example, the rotation matrix which we considered for the second example where the source was Lena image, it is an orthonormal matrix, and now another consideration to choose rotation matrix is to conserve energy. Why this is very important can be explained with the help of an example here. Let us choose an orthogonal matrix A given here, and let us assume that we have the source output vector given by this. Now, the transformation A will give the transform coefficients as shown here. Now, if you look at the energy before rotation, that is squares of this and addition will give you 81, whereas energy after rotation, that is sum of the squares of this elements, will give you 324. So, we do not want such a thing to happen. We want that energy after transformation is also conserved. So, this can be very easily done by scaling the orthogonal matrix by a scale factor. Now, the scaling does not change the fact that the most of the energy is concentrated at the low frequency components. Now, we can formally prove this energy conservation as follows. Energy in the transformed coefficients is given by y I squared I equal to 0 to n minus 1, which can be written in the form of matrix as dot product of y with itself, and this can be rewritten as which can be simplified as follows. Now, if we choose this to be orthonormal matrix, then this is equal to x transpose x dot product of x with itself, which is equal to the energy in the source output vector. So, we choose the linear transform to be orthonormal matrix because it preserves the energy. Now, another reason for choosing this orthonormal matrix is explained in this slide. So, if we use a linear transform, then in principle its inverse can be obtained, but normally it is computationally difficult to get the inverse matrix. But if this transform matrix is orthonormal, then the inverse of the transformation matrix is simply its transpose, and therefore, this has an advantage from the implementation point 2, because the decoder is also a linear transform. And mathematically, it can be shown that orthogonal transform will provide the least minimum squared error as far as the reconstruction is concerned when we throw off some of the transform coefficients. Now, we will not do this, but we will assume this fact and go ahead. So, whatever we have discussed so far can be summarized in this block diagram here. So, in transform coding, blocks of n input samples are transformed to n transform coefficients, which are then quantized individually, and they are either transmitted or stored. At the decoder, an inverse transform is applied to the quantized coefficients, yielding a reconstruction of the original sequence. Now, by designing individual quantizers in accordance with the statistics of their inputs, it is possible to allocate bits in a more optimal manner, example encoding the more important coefficients at a higher bit rate. Now, for our discussion, n by n transform will be any, without loss of generality, real valued linear operation taking n input samples to n output samples or transform coefficients. This operation can be represented in matrix form as follows, where x m vector and y m vectors represent n by 1 blocks of input and output elements respectively, where x m vector is related to the input sequence as follows, and the y m vector is related to the output vector as follows. Now, before we go ahead with the discussion of transform coding, let us recall the quantization error which occurs in pulse code modulation. Pulse code modulation is nothing but discretization of an analog waveform in time or space and amplitude. So, for a given bit rate of r bits per sample, uniformly quantized PCM implies a mean squared quantization error of sigma q squared, which is equivalent to reconstruction error in PCM is equal to delta squared by 12, where delta is obtained by 2 x max divided by L, where L is equal to 2 raised to r. And this we have seen earlier. So, this can be simplified as 1 by 3 x squared max 2 raised to minus 2 r, and this can be rewritten as x squared max by variance of the input multiplied by variance of the input times 2 raised to minus 2 r. Now, this quantity depends on the distribution of x. So, for a uniform quantizer for a given distribution, we can write this quantization error or reconstruction error as gamma x times variance of the input times 2 raised to minus 2 r. So, this constant gamma x depends on the distribution of x. We will utilize this information to find out the optimum bit allocation strategy in transform coding. Now, another question that arises using this strategy is, what is the mean squared reconstruction error? That means, error between the reconstructed sequence and the original sequence. So, this can be written as mean squared reconstruction error is equal to 1 by n summation of k equal to 0 to n minus 1 expectation of this is the mean squared error for a particular component, and since there are n components, we get by definition this expression. Now, this can be simplified as 1 by n expectation of the Euclidean distance between the original vector and the reconstructed vector. This can be rewritten as which can be rewritten as Now, this is the quantized transformed coefficient vector, which is equal to the original transform coefficient vector plus quantization error associated with each component. So, this is another vector minus x m, and this can be further simplified as because y m is equal to transform times x m plus now for orthonormal transform, this quantity is equal to I, and therefore, this reduces to 1 by n expectation of inverse transform of the quantization error, which can be rewritten as now, because T is an orthonormal transform, this is again equal to identity matrix. So, this is equal to 1 time and equal to So, what this result indicates is that mean squared reconstruction error will be denoted as MSE reconstruction is equal to mean squared quantization error, which will be indicated as MSE quantization. And this is true when you have T as an orthonormal transformation matrix. Now, in the example which we discussed earlier, for lossy transform coding application, we threw off all the second components of the transform vector and quantize the first component alone. Now, the natural question is that assuming that transform is an n by n orthonormal matrix, what is the mean squared error optimal bit rate allocation strategy assuming independent uniform quantization of the transform output? In other words, we want to find out the rates for the different quantizer such that it minimize the average reconstruction error for the fixed given average rate. And the next question is, how do we choose this transform itself so that the mean square error reconstruction is minimized? We will try to answer these questions in the next class.